Far out in the icy reaches of our solar system, beyond the familiar planets and the warmth of the sun, lies a world so strange and mysterious that it defies everything we thought we knew about the cosmos. This is Eris, a dwarf planet shrouded in secrets, a place where the rules of science seem to bend and twist in ways that leave even the brightest minds scratching their heads. Discovered in 2005, Eris is not just another frozen rock drifting in the darkness. It's a cosmic enigma, a puzzle box waiting to be unlocked. From its unnaturally bright surface to its bizarre orbit and the whispers of hidden geological activity, Eris challenges our understanding of the universe at every turn. But what makes this distant world so peculiar? What secrets does it hold that could rewrite the story of our solar system? Today, we're diving deep into the 25 most baffling mysteries of Eris, uncovering the questions that have puzzled scientists for decades and exploring the tantalizing clues that might just lead us to the answers. So, buckle up and get ready for a journey to the edge of the known universe where the mysteries of Eris await. Let's begin. Now, let's turn our attention to one of the most striking features of Eris, its mysterious brightness. Out in the Kuiper Belt, where sunlight is faint and distant, Eris stands out as one of the brightest objects. But why? What makes this dwarf planet shine so brilliantly in the darkness of space? The answer lies in its surface. Eris reflects an unusually high amount of sunlight, a phenomenon that has left scientists both fascinated and puzzled. One leading theory points to the presence of methane ice on Eris's surface. Methane ice is highly reflective, acting like a cosmic mirror that bounces sunlight back into space. This could explain why Eris appears so luminous compared to other objects in its neighborhood. But there's more to it than just methane. Some researchers suggest that Eris's surface might also be coated with a thin layer of nitrogen ice, which is even more reflective. Together, these icy materials could create a dazzling sheen that makes Eris one of the brightest objects in the Kuiper Belt. However, the mystery deepens when we consider how Eris maintains such a pristine, reflective surface. Over time, cosmic rays and solar radiation should darken its icy exterior, yet Eris remains strikingly bright. This has led scientists to speculate that Eris might be geologically active, with processes like cryovolcanism or sublimation refreshing its surface and keeping it shiny. Could Eris be hiding a dynamic, ever-changing landscape beneath its icy shell? The answer to this question could reshape our understanding of how distant worlds evolve and interact with their environments. As we continue to unravel the secrets of Eris's brightness, one thing is clear. This dwarf planet is far more than just a frozen relic of the early solar system. It's a world that challenges our assumptions and invites us to look deeper into the mysteries of the cosmos. And speaking of mysteries, let's move on to another intriguing aspect of Eris, its peculiar orbit, which defies the norms of planetary motion. Now, let's take a closer look at the role of methane ice on Eris's surface and how it might be shaping this dwarf planet's dazzling appearance. Methane ice, as we've touched on earlier, is incredibly reflective, but its presence on Eris raises some fascinating questions. For one, how does methane ice survive in such a cold, distant environment? And what does its existence tell us about Eris's geological history? Methane ice is known to be highly volatile, meaning it can easily transition from a solid to a gas when exposed to even slight increases in temperature. Given Eris's extreme distance from the Sun, its surface temperatures hover close to absolute zero, creating the perfect conditions for methane ice to remain stable. But here's where it gets interesting. The presence of methane ice suggests that Eris might have once been closer to the Sun, where temperatures were warmer, allowing methane to exist in a gaseous form. Over time, as Eris migrated outward, the methane could have frozen onto its surface, creating the reflective layer we see today. But methane ice doesn't just sit there passively. It plays an active role in shaping Eris's surface. When exposed to sunlight, even the faint amount that reaches the Kuiper Belt, methane ice can undergo a process called sublimation. This is where the ice turns directly into gas without becoming a liquid first. As this gas escapes into space, it could leave behind fresh, reflective ice, effectively resurfacing parts of Eris and maintaining its brightness. This process might also explain why Eris hasn't been darkened by cosmic rays or solar radiation over billions of years. Its surface is constantly being renewed. The implications of this are profound. If Eris is indeed undergoing sublimation, it suggests that the dwarf planet is geologically active, at least on a surface level. This challenges the traditional view of Kuiper Belt objects as static, unchanging relics of the early solar system. Instead, Eris could be a dynamic world with processes that reshape its surface over time. This raises even more questions. Could there be cryovolcanos on Eris erupting with methane or other ices? Or perhaps subsurface reservoirs of methane that feed this ongoing activity? As we piece together the clues, one thing becomes clear. Methane ice isn't just a passive feature of Eris's surface, it's a key player in the dwarf planet's story. Its presence hints at a complex history and a potentially active present, making Eris a fascinating subject for further study. And as we continue to explore this icy world, we're reminded that even in the farthest reaches of our solar system, there's still so much to discover. Next, we'll delve into another captivating mystery, Eris's peculiar orbit and how it defies the norms of planetary motion. Now, let's shift our focus to another intriguing aspect of Eris, its peculiar orbit. Unlike the relatively circular and flat orbits of most planets and dwarf planets in our solar system, Eris follows a path that's both highly elliptical and significantly tilted. This unusual orbit sets Eris apart, making it a standout object in the Kuiper Belt and raising questions about how such a path came to be. Eris's orbit is so elongated that its distance from the Sun varies dramatically over time. At its closest approach, Eris comes within about 37 astronomical units of the Sun, but at its farthest, it stretches out to nearly 100 astronomical units. To put that into perspective, 1 astronomical unit is the average distance between Earth and the Sun. This means Eris's journey takes it from the outer edges of the Kuiper Belt to the fringes of the scattered disk, a region of space filled with icy objects that have been flung outward by gravitational interactions. Adding to the mystery is the tilt of Eris's orbit, which is inclined at an angle of about 44 degrees relative to the plane of the solar system. Most planets and dwarf planets orbit close to this plane, known as the ecliptic, but Eris's orbit is dramatically off-kilter. This high inclination suggests that Eris didn't form in its current location, but was instead pushed or pulled into this unusual path by some significant force. So, what could have caused Eris to end up with such a strange orbit? One leading theory points to the gravitational influence of Neptune. As the solar system was forming, Neptune's powerful gravity may have disrupted the orbits of smaller objects in the outer regions, sending them into more eccentric and tilted paths. Eris, being one of the largest objects in the Kuiper Belt, could have been particularly affected by these interactions. Over billions of years, these gravitational nudges might have sculpted Eris's orbit into the shape we see today. But Eris's peculiar orbit isn't just a curiosity, it challenges our understanding of how planetary systems form and evolve. Traditionally, we've thought of planetary orbits as relatively stable and orderly, shaped by the gentle pull of the Sun's gravity. Eris's orbit, however, suggests that the outer solar system was far more chaotic in its early days, with massive planets like Neptune playing a disruptive role. This raises questions about how many other objects might have been similarly affected and what their orbits can tell us about the history of our solar system. As we continue to study Eris, its orbit serves as a reminder that the outer reaches of our solar system are anything but predictable. This distant dwarf planet, with its strange and winding path, offers a glimpse into the dynamic and often turbulent processes that shape the worlds around us. Next, we'll explore how Neptune's gravitational influence might have played a key role in shaping Eris's orbit, and what this reveals about the broader dynamics of the outer solar system. Now, let's take a closer look at how Neptune's gravitational influence might have played a pivotal role in shaping Eris's unusual orbit. Neptune, the solar system's outermost giant planet, is a gravitational powerhouse. Its immense pull has long been known to affect the orbits of smaller objects in the Kuiper Belt, and Eris is no exception. Scientists believe that during the early days of the solar system, Neptune's gravity could have acted like a cosmic slingshot, flinging objects like Eris into their current eccentric and tilted path. One key piece of evidence supporting this theory lies in the way Neptune interacts with other Kuiper Belt objects. Many of these icy bodies, including Eris, share similar orbital characteristics, high inclinations, and elongated shapes. This suggests that Neptune's gravitational influence wasn't limited to just one or two objects, but was a widespread phenomenon. As Neptune migrated outward during the solar system's formation, its gravity likely disturbed the orbits of countless smaller bodies, sending them into chaotic trajectories. Eris, being one of the largest and most distant of these objects, would have been particularly susceptible to these gravitational nudges. But what does this tell us about the broader dynamics of the outer solar system? For one, it highlights the chaotic and unpredictable nature of this region during its formative years. Unlike the relatively stable inner solar system, where planets like Earth and Mars settled into nearly circular orbits, the outer solar system was a battleground of gravitational forces. Neptune's migration and its interactions with smaller objects like Eris provide a window into this turbulent past, showing how the outer solar system was shaped by a series of dramatic events. Moreover, Eris's orbit serves as a reminder that the Kuiper Belt is far from a static collection of icy debris. It's a dynamic region where gravitational interactions continue to play out, even billions of years after the solar system's formation. By studying Eris and its orbit, scientists can piece together a more complete picture of how the outer solar system evolved and how it continues to change over time. As we move forward, this understanding of Neptune's influence not only helps explain Eris's peculiar orbit, but also sheds light on the broader processes that shape the outer solar system. Next, we'll turn our attention to another fascinating aspect of Eris, the debate surrounding its size and how it compares to Pluto, a topic that has sparked significant controversy in the astronomical community. Now, shifting our focus to another intriguing aspect of Eris, let's dive into the heated debate surrounding its size, a topic that has sparked significant controversy in the astronomical community. When Eris was first discovered in 2005, initial observations suggested it might be larger than Pluto, a claim that sent shockwaves through the scientific world. This revelation played a key role in the eventual reclassification of Pluto as a dwarf planet, as it raised questions about how we define what constitutes a planet. At the time, astronomers used Eris's brightness as a proxy for its size, assuming that a brighter object must be larger. However, this assumption turned out to be more complicated than anticipated. Eris's surface, covered in highly reflective methane ice, made it appear much brighter than it might otherwise be, leading to overestimations of its size. As more advanced measurement techniques became available, including precise observations from ground-based telescopes and data from the New Horizons mission to Pluto, scientists began to refine their estimates. These new measurements revealed that Eris is, in fact, slightly smaller than Pluto in terms of diameter. However, it's important to note that Eris is significantly denser, suggesting a different internal composition. This density implies that Eris may have a larger rocky core compared to Pluto, which could have implications for its formation and evolution. The discovery of Eris's true size not only reshaped our understanding of this distant world, but also highlighted the challenges of measuring objects in the far reaches of the solar system. The size debate also underscores a broader issue in planetary science: the difficulty of defining what makes a planet. Eris's discovery forced astronomers to reconsider the criteria for planetary classification, leading to the creation of the dwarf planet category. This reclassification was met with both excitement and resistance, as it challenged long-held assumptions about the solar system's structure. As we continue to explore Eris and other Kuiper Belt objects, the size debate serves as a reminder of how much we still have to learn about these distant worlds. Next, we'll examine how the New Horizons mission provided critical insights into Eris's size and what this means for our understanding of the outer solar system. Now, let's turn our attention to the groundbreaking role of the New Horizons mission in shedding light on Eris's true size. When New Horizons flew past Pluto in 2015, it provided an unprecedented level of detail about the dwarf planet's surface, atmosphere, and dimensions. This wealth of data didn't just transform our understanding of Pluto. It also had a ripple effect on how we perceive Eris and other distant objects in the Kuiper Belt. One of the key contributions of New Horizons was its ability to measure Pluto's size with remarkable precision. By comparing these measurements to earlier estimates of Eris's size, scientists were able to recalibrate their understanding of both objects. Before New Horizons, Eris was thought to be larger than Pluto, but the mission's findings revealed that Pluto is, in fact, slightly bigger in diameter. This discovery was a game-changer, as it forced astronomers to revisit their assumptions about Eris's physical characteristics. The mission also highlighted the importance of direct observation. While ground-based telescopes had provided valuable data, they were limited by the vast distances and the reflective properties of Eris's surface. New Horizons, on the other hand, offered a close-up view of Pluto, allowing scientists to refine their models and apply these insights to Eris. This indirect approach demonstrated how studying one object could enhance our understanding of another, even when direct observation isn't possible. Beyond size, the New Horizons mission underscored the complexity of planetary classification. By revealing the diversity of objects in the Kuiper Belt, it reinforced the idea that size alone isn't enough to define a planet. Factors like orbital characteristics, composition, and geological activity also play crucial roles. This broader perspective has helped astronomers appreciate the unique nature of Eris, which, despite being smaller than Pluto, remains one of the most intriguing objects in the outer solar system. As we look to the future, the legacy of New Horizons continues to inspire. Its success has paved the way for potential missions to Eris and other distant worlds, promising even more discoveries that could reshape our understanding of the solar system. Next, we'll explore Eris's moon, Dysnomia, and how this enigmatic companion adds another layer of mystery to this already fascinating dwarf planet. Now, shifting our gaze to the skies above Eris, we encounter Dysnomia, the solitary moon that orbits this distant dwarf planet. Named after the Greek goddess of lawlessness, Dysnomia is as enigmatic as its namesake, offering tantalizing clues about Eris's history and formation. Discovered in 2005, the same year as Eris itself, Dysnomia has since become a focal point for astronomers seeking to unravel the mysteries of this icy world. One of the most striking aspects of Dysnomia is its size relative to Eris. While most moons in the solar system are significantly smaller than their parent planets, Dysnomia is unusually large compared to Eris. In fact, it's estimated to be about 1/8 the size of Eris, making it one of the largest known moon-to-planet ratios in our solar system. This unusual proportion raises intriguing questions about how Dysnomia formed. Some scientists speculate that it might be the result of a colossal collision between Eris and another Kuiper Belt object, with Dysnomia being the leftover debris from that ancient impact. If true, this would provide valuable insights into the chaotic early days of the solar system. Dysnomia's orbit around Eris is another area of fascination. Unlike many moons that follow nearly circular paths, Dysnomia's orbit is slightly elliptical, adding another layer of complexity to its relationship with Eris. This irregular orbit suggests that Dysnomia's formation and subsequent gravitational interactions with Eris were anything but straightforward. By studying the dynamics of this moon, astronomers can infer details about Eris's mass, density, and internal structure, which are otherwise difficult to measure directly from such a vast distance. The presence of dysnomia also has broader implications for our understanding of the Kuiper Belt. Its existence hints that other large objects in this region might also have moons, potentially revealing a hidden population of binary systems. This could reshape our understanding of how objects in the outer solar system form and evolve over time. As we continue to explore Dysnomia's peculiarities, it becomes clear that this moon is more than just a companion to Eris. It's a key piece of the puzzle in understanding the dwarf planet's origins and the history of the Kuiper Belt. Next, we'll delve deeper into the mysteries of Dysnomia's orbit and what it reveals about the gravitational dance between these two distant worlds. Now, let's take a closer look at the peculiarities of Dysnomia's orbit and what it tells us about Eris. Dysnomia's path around Eris is not only elliptical but also remarkably slow, taking about 16 Earth days to complete a single orbit. This leisurely pace is unusual for a moon, especially one so far from the Sun, and it provides critical clues about the gravitational relationship between Dysnomia and Eris. The slow rotation suggests that Dysnomia is tidally locked, meaning the same side of the moon always faces Eris, much like our own moon does with Earth. This locking effect is a result of gravitational forces over billions of years, and it hints at the immense mass and density of Eris itself. The shape of Dysnomia's orbit also offers insights into Eris's internal structure. The slight ellipticity of the orbit indicates that Eris is not a perfectly uniform sphere. Instead, it likely has a dense, rocky core surrounded by a thick layer of ice. This combination of materials would create subtle gravitational irregularities, tugging on Dysnomia in ways that shape its orbit. By analyzing these gravitational interactions, scientists can estimate Eris's mass and density, even from billions of miles away. Surprisingly, Eris's density appears to be higher than that of Pluto, suggesting it has a greater proportion of rock in its composition. This raises intriguing questions about how Eris formed and whether it experienced a different evolutionary path compared to other dwarf planets. Another fascinating aspect of Dysnomia's orbit is its stability. Despite its elliptical shape, the orbit remains remarkably consistent over time, with no signs of significant wobbling or decay. This stability suggests that Dysnomia and Eris have been locked in their gravitational dance for billions of years, undisturbed by external forces. Such a long-standing relationship provides a rare window into the early solar system, offering clues about the conditions and processes that shape the Kuiper Belt. As we piece together the story of Dysnomia's orbit, it becomes clear that this moon is more than just a silent companion. It's a dynamic partner in Eris's cosmic journey. The slow, elliptical path it traces around Eris reveals not only the dwarf planet's mass and density, but also the intricate gravitational forces at play in the outer reaches of our solar system. Next, we'll turn our attention to the surface of Eris itself, exploring what little we know about this icy world and the secrets it might still be hiding. Now, shifting our focus to the surface of Eris, we find ourselves staring at one of the most enigmatic landscapes in the solar system. Eris's surface is a frozen expanse, dominated by a thick layer of ice that reflects sunlight with remarkable brightness. This icy shell is thought to be composed primarily of methane and nitrogen ices, which give Eris its strikingly white appearance. But beneath this icy veneer lies a world of mystery, with clues suggesting that Eris's surface might not be as static as it seems. One of the most intriguing possibilities is the presence of cryovolcanism, a phenomenon where volcanoes erupt not with molten rock, but with icy materials like water, ammonia, or methane. On Eris, the extreme cold and distance from the sun make traditional volcanic activity impossible, but cryovolcanism could still occur. If Eris has a warm enough interior, perhaps due to radioactive decay or tidal heating from its interactions with dysnomia, it could generate enough pressure to push icy material to the surface. This would create a dynamic, ever-changing landscape, with cryovolcanoes potentially reshaping Eris's surface over time. Another fascinating aspect of Eris's surface is its potential for other forms of geological activity. The dwarf planet's high density suggests a rocky core, which could generate internal heat and drive processes like tectonic shifts or the formation of icy plains. While we have no direct evidence of such activity yet, the possibility remains tantalizing. Future missions equipped with advanced imaging technology could reveal surface features like cracks, ridges, or even frozen lakes, offering a glimpse into Eris's geological history. Observing Eris's surface from Earth, however, is no easy task. Its immense distance and small size make it a challenging target for even the most powerful telescopes. What little we know comes from studying the way light reflects off its surface and analyzing its brightness variations. These observations suggest that Eris's surface is relatively smooth with few large craters. This could indicate that its surface is young, having been resurfaced by cryovolcanic activity or other processes in the recent past. As we continue to unravel the secrets of Eris's surface, one thing is clear: this distant world is far more complex than it appears. Its icy exterior hides a wealth of potential geological activity waiting to be discovered. Next, we'll delve into the challenges of observing Eris's surface in greater detail and explore how future missions might uncover the hidden features of this frozen frontier. Now, let's turn our attention to the ongoing efforts to uncover the secrets of Eris's surface. Despite the challenges posed by its immense distance from Earth, scientists are determined to learn more about this distant world. Observing Eris's surface features is no small feat. Even with the most advanced telescopes, the dwarf planet appears as little more than a faint, shimmering dot in the vast expanse of space. Its small size and extreme distance make it incredibly difficult to resolve any detailed surface features from Earth. Most of what we know comes from indirect methods, such as analyzing the way light reflects off its surface and studying its brightness variations over time. These observations have revealed that Eris's surface is surprisingly smooth, with few large craters. This smoothness suggests that its surface might be relatively young, having been resurfaced by geological processes like cryovolcanism or tectonic activity. However, without direct imaging, we can only speculate about the exact nature of these features. Are there towering cryovolcanoes, vast icy plains, or deep fractures crisscrossing its surface? The answers remain hidden, waiting for future missions to bring them to light. The potential for future exploration is where things get truly exciting. Imagine a spacecraft equipped with high-resolution cameras and advanced instruments, flying by Eris and capturing detailed images of its surface. Such a mission could reveal surface features in stunning clarity, providing insights into its geological history and activity. For instance, we might discover evidence of cryovolcanic eruptions, frozen lakes, or even ancient impact basins. These findings could revolutionize our understanding of not just Eris, but also other icy worlds in the Kuiper Belt. One of the biggest challenges, however, is the sheer distance involved. Eris is so far from the Sun that it takes sunlight more than 9 hours to reach it. This means any mission to Eris would require cutting-edge technology to withstand the extreme cold and darkness of the outer solar system. Additionally, the journey itself would take years, requiring careful planning and patience. But the rewards could be immense, offering a treasure trove of data about this mysterious dwarf planet. As we look to the future, the search for Eris's surface features represents a thrilling frontier in planetary exploration. With each new discovery, we inch closer to understanding the complex processes that shape these distant worlds. Next, we'll explore the extreme temperatures of Eris and how its frigid environment influences its physical and chemical properties, adding yet another layer to the mysteries of this icy enigma. Now, let's venture into the icy realm of Eris's temperature, a world so cold it defies imagination. Eris is one of the coldest places in our solar system, with surface temperatures plummeting to nearly -240 degrees Celsius. To put that into perspective, that's just a few dozen degrees above absolute zero, the coldest temperature possible in the universe. At such extreme lows, the very nature of matter changes, and Eris becomes a frozen laboratory for understanding how materials behave in these harsh conditions. The frigid temperatures on Eris have a profound impact on its physical and chemical properties. For instance, the ice on its surface isn't just water ice, it's likely a mix of frozen methane, nitrogen, and other volatile compounds. These ices behave differently under such extreme cold, becoming incredibly hard and brittle. Imagine trying to walk on a surface where even the slightest pressure could cause the ice to crack and shatter like glass. This brittleness could explain why Eris's surface appears so smooth, as any impacts or geological activity might cause the ice to fracture and refreeze over time. But the cold doesn't just affect the surface, it also influences Eris's internal structure. At these temperatures, materials contract, becoming denser and more rigid. This could mean that Eris's rocky core, if it exists, is under immense pressure, surrounded by layers of ice that have been compressed to an almost crystalline state. The extreme cold also slows down chemical reactions to a near standstill, preserving Eris's surface in a kind of deep freeze time capsule. This makes it a fascinating target for scientists studying the early solar system, as its surface might hold clues to the conditions that existed billions of years ago. The cold also plays a role in Eris's potential for geological activity. While it might seem counterintuitive, some scientists speculate that the extreme temperatures could actually drive cryovolcanism, eruptions of icy materials instead of molten rock. The intense cold could create pockets of pressurized gases beneath the surface, which, when released, might erupt in spectacular icy plumes. While we haven't observed this directly, the possibility adds another layer of intrigue to this already mysterious world. As we continue to explore the mysteries of Eris, its extreme temperatures remind us just how alien and unforgiving the outer solar system can be. Next, we'll delve into how Eris's vast distance from the Sun contributes to its frigid environment and what this means for its potential habitability or lack thereof. Now, let's turn our attention to the role of distance in shaping Eris's icy reality. Eris orbits the Sun at an average distance of about 6,700,000,000 miles, making it one of the most remote objects in our solar system. To put that into perspective, it's more than twice as far from the Sun as Pluto. This staggering distance means that sunlight reaching Eris is incredibly faint, providing only a fraction of the warmth we experience here on Earth. In fact, the Sun would appear as little more than a bright star in Eris's sky, offering almost no heat to its frozen surface. This extreme distance is the primary reason Eris is so cold. With so little solar energy to warm it, the dwarf planet remains locked in a perpetual deep freeze. The lack of heat also means that any potential atmosphere Eris might have would be incredibly thin, if it exists at all. Without the warmth to keep gases in a stable state, they would either freeze onto the surface or escape into space. This makes the idea of habitability on Eris seem almost impossible. As life as we know it requires a stable environment with liquid water and a protective atmosphere, conditions that Eris simply cannot provide. However, the distance from the Sun doesn't just affect Eris's temperature, it also influences its ability to retain heat. Unlike planets closer to the Sun, which can store warmth in their cores or atmospheres, Eris has no such luxury. Any heat generated internally, perhaps from radioactive decay or tidal forces, would quickly dissipate into the void of space. This leaves Eris in a state of constant cold, with no significant source of energy to drive geological or chemical processes. Yet, despite these harsh conditions, Eris's distance from the Sun offers a unique opportunity for scientists. Its remote location means it has been relatively undisturbed since the early days of the solar system, preserving clues about the formation and evolution of our cosmic neighborhood. Studying Eris could help us understand how objects in the outer solar system formed and why they ended up in such distant orbits. As we reflect on Eris's frigid existence, it's clear that its distance from the Sun plays a defining role in shaping its environment. This icy world stands as a testament to the extremes of our solar system, reminding us just how diverse and mysterious the cosmos can be. Next, we'll explore the story of Eris's discovery and the controversy it sparked over Pluto's planetary status, a tale that reshaped our understanding of the solar system. Now, let's journey back to the year 2005, a pivotal moment in astronomy that forever changed our understanding of the solar system. It was during this time that Eris, the distant dwarf planet, was discovered by a team led by astronomer Mike Brown at the Palomar Observatory in California. This discovery wasn't just another addition to the list of celestial objects. It ignited a fiery debate that would reshape the way we define planets. Eris was initially thought to be larger than Pluto, a fact that sent shockwaves through the scientific community. If Eris was bigger, then what did that mean for Pluto's status as the ninth planet? The discovery forced astronomers to confront a question that had been simmering for years: what exactly makes a planet a planet? The International Astronomical Union, the governing body for such classifications, found itself at the center of a heated discussion. After much deliberation, they made a historic decision in 2006, introducing a new definition that required a planet to clear its orbit of other debris. Pluto, which shares its orbital neighborhood with other objects in the Kuiper Belt, no longer met the criteria. Along with Eris, it was reclassified as a dwarf planet. This decision was met with mixed reactions. Some celebrated it as a necessary step toward scientific clarity, while others mourned the demotion of Pluto, a celestial body that had long held a special place in popular culture. The controversy even spilled over into public discourse, with debates raging in classrooms, newsrooms, and dinner tables around the world. Eris, named after the Greek goddess of discord, lived up to its name by sparking this cosmic upheaval. But beyond the controversy, Eris's discovery marked a turning point in our exploration of the outer solar system. It highlighted the existence of a whole new class of objects in the Kuiper Belt, challenging us to rethink our assumptions about planetary formation and classification. As we continue to uncover more about Eris and its distant neighbors, we're reminded that the universe is full of surprises, waiting to reshape our understanding of the cosmos. Next, we'll delve into the significance of Eris's name and how it reflects the turmoil it caused in the astronomical community, a story that ties mythology to modern science in a fascinating way. Now, let's turn our attention to the name itself, Eris. This distant dwarf planet wasn't just given any random name. It was deliberately chosen to reflect the chaos it brought to the world of astronomy. In Greek mythology, Eris is the goddess of discord and strife, known for sowing conflict and rivalry among gods and mortals alike. Her most famous act was tossing the golden apple inscribed with the words "to the fairest" into a gathering of gods, sparking the events that led to the Trojan War. It's a fitting namesake for a celestial body that, upon its discovery, threw the astronomical community into disarray. The naming of Eris wasn't just a nod to mythology, it was a statement. By choosing a name associated with upheaval and controversy, astronomers acknowledge the profound impact this discovery had on our understanding of the solar system. The debate over Pluto's planetary status, fueled by Eris's size and characteristics, was nothing short of a scientific revolution. It forced us to rethink long-held definitions and classifications, challenging the very framework we use to understand the cosmos. In many ways, Eris became a symbol of how new discoveries can disrupt even the most established ideas. But there's more to the name than just its mythological roots. Eris also represents the spirit of exploration and the willingness to question what we think we know. Its discovery reminded us that the universe is far more complex and unpredictable than we often assume. By naming it after a goddess of discord, astronomers highlighted the importance of embracing uncertainty and being open to change, a lesson that resonates far beyond the realm of science. As we continue to study Eris and its place in the Kuiper Belt, its name serves as a reminder of the dynamic and ever-evolving nature of our understanding of the cosmos. Next, we'll explore another intriguing aspect of this distant world, its surprisingly high density and what it reveals about the secrets hidden beneath its icy surface. Now, let's shift our focus to one of Eris's most puzzling characteristics: its density. Despite being an icy world in the far reaches of the solar system, Eris has a surprisingly high density, which hints at something unexpected beneath its frozen surface. Most objects in the Kuiper Belt are composed primarily of ice and rock, but Eris's density suggests it has a much larger proportion of rock than its neighbors. This raises intriguing questions about what lies beneath its icy shell. Scientists believe that Eris's high density points to the presence of a rocky core, possibly surrounded by a thick layer of ice. This combination of materials is unusual for a dwarf planet in the Kuiper Belt, where most objects are thought to be less dense and more ice-dominated. The presence of a rocky core suggests that Eris may have formed differently than other Kuiper Belt objects, or that it underwent significant changes during its early history. Could it have experienced intense collisions or internal heating that caused heavier materials to sink to its center? These are the kinds of mysteries that keep astronomers intrigued. The density of Eris also provides clues about its internal structure. A rocky core would mean that Eris has a more complex geology than we might expect from a distant, icy world. It could even hint at the possibility of geological activity beneath the surface, such as the movement of ice or the presence of subsurface oceans. While we don't yet have direct evidence of such activity, the density measurements open up exciting possibilities for future exploration. Understanding Eris's density isn't just about solving a scientific puzzle, it's about piecing together the story of how this distant world came to be. By studying its internal structure, we gain insights into the processes that shape not only Eris but also the broader Kuiper Belt. As we continue to unravel the secrets of this enigmatic dwarf planet, its density serves as a reminder that even the most distant objects in our solar system can hold surprising and profound truth. Next, we'll compare Eris's density to that of Pluto, exploring what these two worlds can teach us about the diversity of the Kuiper Belt. Now, let's take a closer look at how Eris stacks up against its famous neighbor, Pluto. Both Eris and Pluto are dwarf planets in the Kuiper Belt, and they share some striking similarities, but their differences are just as fascinating. When it comes to density, Eris and Pluto tell two very different stories about their origins and evolution. Eris's density is significantly higher than Pluto's, which suggests that Eris has a much larger proportion of rock in its composition. While Pluto is also thought to have a rocky core, its overall density is lower, indicating a greater amount of ice in its structure. This difference raises intriguing questions about how these two worlds formed. Did Eris start with more rocky material, or did it lose more of its ice over time? The answers could shed light on the chaotic early days of the Kuiper Belt. Another key difference lies in their surfaces. Pluto's surface is a patchwork of icy plains, mountains, and even glaciers, while Eris's surface appears much brighter and more uniform. This brightness is likely due to a layer of methane ice, which reflects sunlight more effectively than the mix of ices found on Pluto. The contrast between their surfaces hints at different geological histories, with Eris possibly experiencing less recent activity than Pluto. Despite these differences, both Eris and Pluto share a common trait: they challenge our understanding of what it means to be a planet. Their densities, compositions, and orbits all point to a complex and dynamic history that defies simple categorization. By comparing these two worlds, scientists can piece together a more complete picture of the Kuiper Belt and the processes that shaped it. As we continue to explore these distant worlds, the comparison between Eris and Pluto reminds us of the incredible diversity within our solar system. Each object, no matter how small or distant, has a unique story to tell. Next, we'll turn our attention to another tantalizing mystery. Could Eris have an atmosphere despite its extreme distance from the Sun? Stay tuned as we dive into this intriguing possibility. Now, let's shift our focus to one of the most intriguing questions about Eris. Could this distant dwarf planet actually have an atmosphere? At first glance, the idea seems almost impossible. Eris orbits the Sun at an average distance of nearly 6,800,000,000 miles, making it one of the coldest places in the solar system. With surface temperatures hovering close to absolute zero, it's hard to imagine any gases lingering around Eris for long. Yet, scientists have begun to wonder if a thin, tenuous atmosphere might exist even under such extreme conditions. The possibility hinges on Eris's composition. Like Pluto, Eris is thought to have a surface rich in volatile ices such as methane and nitrogen. When exposed to even the faintest warmth from the Sun, these ices can sublimate, turning directly from solid to gas, creating a temporary atmosphere. On Pluto, this process is well documented, with its thin atmosphere expanding and contracting as it moves closer to or farther from the Sun. Could Eris experience something similar? The challenge lies in detecting such an atmosphere. Eris's distance makes it incredibly difficult to observe directly, and any atmosphere it might have would be far thinner than Pluto's. However, some clues suggest it's not entirely out of the question. For instance, Eris's bright, reflective surface could indicate the presence of fresh methane ice, which might sublimate under the right conditions. Additionally, if Eris has any internal heat, perhaps from radioactive decay or tidal forces, it could help sustain a faint atmosphere even in the frigid depths of the Kuiper Belt. If Eris does have an atmosphere, it would have profound implications for our understanding of this distant world. A thin layer of gas could influence surface conditions, potentially smoothing out terrain or redistributing ices over time. It might also provide clues about Eris's geological activity, hinting at processes that could be shaping its surface even today. Of course, the mystery of Eris's atmosphere remains unsolved. Without more data from close-up observations, we can only speculate, but the tantalizing possibility keeps scientists curious, driving the search for answers about this enigmatic dwarf planet. Next, we'll explore the challenges of detecting an atmosphere on Eris and the technologies that might help us uncover the truth. Stay with us as we delve deeper into this fascinating mystery. Now, let's turn our attention to the challenges scientists face in detecting an atmosphere on Eris. Despite the tantalizing possibility, confirming its existence is no easy task. The sheer distance of Eris from Earth makes direct observation incredibly difficult. Even with the most advanced telescopes, the faint signals that might indicate an atmosphere are often drowned out by the vast emptiness of space. This means that traditional methods of atmospheric detection, like spectroscopy, are pushed to their limits when applied to such a distant and dim object. Another major hurdle is the potential thinness of Eris's atmosphere. If it exists, it's likely to be far more tenuous than Pluto's, which itself is already incredibly sparse. Detecting such a faint layer of gas requires instruments with extraordinary sensitivity, capable of picking up the subtlest of signals. Current technology, while impressive, struggles to provide the level of detail needed to definitively confirm or rule out the presence of an atmosphere on Eris. To overcome these challenges, scientists are looking to future missions and advancements in observational technology. Spacecraft equipped with specialized instruments could one day venture close enough to Eris to study its atmosphere directly. These missions would need to carry tools capable of analyzing the faint traces of gas that might surround the dwarf planet, as well as instruments to measure surface composition and temperature in unprecedented detail. Such a mission would not only answer the question of Eris's atmosphere, but also provide a wealth of new information about this mysterious world. In the meantime, astronomers are refining their techniques for remote observation. By combining data from multiple telescopes and using innovative methods to filter out noise, they hope to catch glimpses of Eris's potential atmosphere. Every new observation brings us a step closer to understanding whether this distant dwarf planet holds onto a whisper-thin layer of gas, or if its surface remains exposed to the vacuum of space. As we continue to push the boundaries of our technology and knowledge, the mystery of Eris's atmosphere remains a compelling challenge. It's a reminder of how much we still have to learn about the outer reaches of our solar system. Next, we'll explore Eris's role in the Kuiper Belt and how it fits into the broader picture of this distant region. Stay tuned as we uncover more about this icy enigma. Now, shifting our gaze to the broader cosmic neighborhood, let's explore Eris's role in the Kuiper Belt. This icy dwarf planet isn't just a solitary wanderer, it's a key player in one of the most intriguing regions of our solar system. The Kuiper Belt, a vast ring of icy bodies beyond Neptune, is home to countless objects, each holding clues to the early days of our solar system. Eris, as one of the largest and brightest members of this distant family, offers a unique window into the dynamics and history of this remote region. Eris's interactions with other Kuiper Belt objects are particularly fascinating. Its highly elliptical and tilted orbit suggests a history of gravitational tugs and collisions, possibly influenced by the movements of Neptune or other massive bodies. These interactions have likely shaped not only Eris's path, but also the orbits of smaller objects around it. By studying Eris, scientists can piece together how these distant worlds influence one another, shedding light on the chaotic processes that shaped the outer solar system billions of years ago. Moreover, Eris's size and brightness make it a standout figure in the Kuiper Belt. Its discovery in 2005 challenged our understanding of what constitutes a planet and led to the reclassification of Pluto. This event sparked a broader conversation about the nature of objects in the Kuiper Belt and how they fit into our solar system's architecture. Eris's prominence has also fueled efforts to discover other large objects in this region, pushing the boundaries of our knowledge and technology. But Eris's influence doesn't stop there. Its composition and surface properties provide valuable insights into the conditions of the early solar system. The presence of methane ice and its high reflectivity suggest that Eris has remained relatively unchanged since its formation, acting as a cosmic time capsule. By studying Eris, scientists can better understand the processes that shape not only the Kuiper Belt but also the entire solar system. As we continue to explore this distant region, Eris remains a focal point for discovery. Its mysteries challenge our assumptions and drive us to develop new tools and techniques for studying the outer reaches of our cosmic neighborhood. Next, we'll delve into the search for other Eris-like objects in the Kuiper Belt, uncovering how these discoveries are reshaping our understanding of this icy frontier. Stay with us as we journey deeper into the unknown, turning our attention to the ongoing quest for discovery. scientists are actively searching for other Eris-like objects in the Kuiper Belt. This search isn't just about finding more distant worlds, it's about uncovering the secrets of our solar system's early days. Eris, with its unique size, brightness, and composition, has set a benchmark for what we might expect to find in this icy frontier. As astronomers scan the skies, they're not only looking for objects that resemble Eris, but also for clues about how these distant bodies formed and evolved. One of the most exciting aspects of this search is the potential to find objects that could rival or even surpass Eris in size. While Eris is currently one of the largest known Kuiper Belt objects, there's always the possibility that something even bigger is lurking in the shadows. These discoveries could reshape our understanding of the Kuiper Belt structure and the processes that shaped it. Each new find brings us closer to piecing together the puzzle of our solar system's history. Advanced telescopes and observational techniques are playing a crucial role in this endeavor. Instruments like the Hubble Space Telescope and ground-based observatories equipped with adaptive optics are pushing the boundaries of what we can see. These tools allow astronomers to detect faint, distant objects that would have been invisible just a few decades ago. As technology continues to improve, the chances of discovering more Eris-like objects increase, opening up new avenues for exploration and research. But the search isn't just about size. Scientists are also interested in finding objects with similar surface compositions and orbital characteristics. For example, the presence of methane ice on Eris has sparked curiosity about whether other Kuiper Belt objects might share this feature. By comparing these distant worlds, researchers can gain insights into the chemical and physical processes that have shaped them over billions of years. This comparative approach helps us understand not just individual objects but the Kuiper Belt as a whole. The discovery of other Eris-like objects also has implications for planetary classification. Just as Eris's discovery led to the redefinition of what constitutes a planet, finding more large Kuiper Belt objects could further challenge our understanding of these categories. Each new discovery forces us to rethink our assumptions and refine our definitions, keeping the field of planetary science dynamic and ever-evolving. As we continue to explore the Kuiper Belt, the search for Eris-like objects remains a thrilling and essential part of the journey. These discoveries not only expand our knowledge of the outer solar system, but also remind us of how much we still have to learn. Next, we'll delve into the mystery of Eris's striking white color and what it reveals about this distant world. Stay tuned as we uncover more secrets of the Kuiper Belt's enigmatic giant. Now, let's turn our gaze to one of Eris's most striking features, its brilliant white color. Unlike many other objects in the Kuiper Belt, which often appear darker or more muted, Eris stands out as a gleaming, almost pristine white. This unusual brightness has puzzled scientists and sparked a deeper investigation into what makes Eris so distinct. The key to understanding Eris's color lies in its surface composition. Observations suggest that its surface is covered in a thick layer of highly reflective methane ice. This icy coating acts like a mirror, bouncing back a significant amount of sunlight and giving Eris its dazzling appearance. But why does Eris have so much methane ice compared to other Kuiper Belt objects? The answer may lie in its history. Eris's surface could have been shaped by processes like cryovolcanism, where icy materials erupt from beneath the surface, or by the slow accumulation of frozen gases over billions of years. These processes might have created a surface that's not only icy but also remarkably uniform, contributing to its bright white hue. Another factor that could explain Eris's color is its distance from the Sun. Being so far out in the solar system, Eris experiences extremely cold temperatures, which help preserve its icy surface. Unlike objects closer to the Sun, where heat can cause ices to sublimate or darken over time, Eris's frozen environment keeps its surface relatively unchanged. This preservation allows its reflective properties to remain intact, making it one of the brightest objects in the Kuiper Belt. But Eris's color isn't just a matter of surface composition. It also tells us something about its age and exposure to cosmic forces. Over time, cosmic rays and micrometeorite impacts can darken the surfaces of distant objects. The fact that Eris remains so white suggests that its surface might be relatively young, or that ongoing processes are refreshing its icy layer. This could mean that Eris is geologically active in some way, with mechanisms that resurface or replenish its icy exterior. The mystery of Eris's color also ties into broader questions about the Kuiper Belt. Why do some objects appear dark while others, like Eris, shine so brightly? The answer could lie in the diversity of materials and processes at work in this distant region. By studying Eris's surface, scientists hope to uncover clues about the conditions that shape not just this dwarf planet but the entire Kuiper Belt. As we continue to explore Eris's enigmatic features, its striking white color serves as a reminder of how much we still have to learn about this distant world. Next, we'll dive into the role of cosmic rays in shaping Eris's surface and what this means for its long-term evolution. Stay with us as we uncover more secrets of this icy giant. Now, let's take a closer look at how cosmic rays might be shaping Eris's surface and influencing its striking white color. Cosmic rays are high-energy particles that travel through space, constantly bombarding objects in the solar system. Over time, these particles can interact with the surface materials of distant worlds, altering their composition and appearance. For Eris, this process could be key to understanding why it remains so bright compared to other objects in the Kuiper Belt. When cosmic rays hit Eris's icy surface, they can cause chemical changes in the methane ice. These interactions might break down the methane molecules, creating new compounds that could darken the surface over time. However, Eris's surface remains remarkably white, suggesting that something is counteracting this darkening effect. One possibility is that Eris's surface is being refreshed or resurfaced by geological activity, such as cryovolcanism or the slow movement of icy materials. This could mean that while cosmic rays are constantly bombarding Eris, ongoing processes are effectively erasing the damage, keeping its surface bright and reflective. Another factor to consider is the role of Eris's extreme distance from the Sun. The lack of solar heat means that any changes caused by cosmic rays happen very slowly. Unlike objects closer to the Sun, where heat can accelerate chemical reactions, Eris's frigid environment slows down these processes, giving its surface a chance to remain relatively unchanged for long periods. This could explain why Eris's color has remained so consistent over time, even as cosmic rays continue to bombard it. The interplay between cosmic rays and Eris's surface also raises questions about the age of its icy layer. If cosmic rays are constantly altering the surface, the fact that Eris remains so white suggests that its icy exterior might be younger than we think, or that it's being replenished by internal processes. This could point to a dynamic world beneath its frozen shell, with mechanisms that keep its surface fresh and reflective. Understanding the role of cosmic rays on Eris not only helps us explain its unique color, but also provides insights into the broader processes at work in the Kuiper Belt. By studying how cosmic rays affect Eris, scientists can learn more about the evolution of other distant objects and the conditions that shape their surfaces. As we continue to unravel the mysteries of Eris, the influence of cosmic rays serves as a fascinating piece of the puzzle, reminding us of the complex forces at play in the outer reaches of our solar system. Next, we'll explore another intriguing aspect of Eris, its slow rotation and what it reveals about this distant world's internal structure and history. Stay tuned as we uncover more secrets of this enigmatic dwarf planet. Now, let's turn our attention to another fascinating feature of Eris, its slow rotation. Unlike many other objects in the solar system, Eris takes about 25 hours to complete a single rotation. This leisurely spin offers intriguing clues about the dwarf planet's internal structure and its past interactions with other celestial bodies. A slow rotation like Eris's can tell us a lot about its internal makeup. For one, it suggests that Eris might have a dense, rocky core beneath its icy exterior. The distribution of mass within a planet or dwarf planet plays a significant role in how quickly it spins. If Eris's mass is concentrated toward its center, it could explain why its rotation is more sluggish compared to smaller, less dense objects. This aligns with earlier discussions about Eris's surprisingly high density, hinting at a complex internal structure that sets it apart from other Kuiper Belt objects. Another possibility is that Eris's rotation has been slowed down by collisions in its distant past. In the chaotic early days of the solar system, collisions between objects were far more common. A significant impact could have altered Eris's spin, leaving it with the slow rotation we observe today. This idea ties into the broader story of how the outer solar system evolved, with massive collisions shaping the orbits, spins, and even the compositions of distant worlds like Eris. Interestingly, Eris's rotation also raises questions about its relationship with its moon, Dysnomia. The gravitational tug between Eris and Dysnomia could be influencing the dwarf planet's spin, gradually slowing it down over time. This dynamic interaction between a dwarf planet and its moon is not uncommon, but in Eris's case, it adds another layer of mystery to an already enigmatic world. Understanding how Dysnomia affects Eris's rotation could provide valuable insights into the formation and evolution of binary systems in the Kuiper Belt. The slow rotation of Eris also has implications for its surface conditions. A longer day-night cycle means that different parts of the dwarf planet are exposed to sunlight for extended periods, which could influence surface temperatures and even geological processes. For example, areas that remain in shadow for longer might retain more ice, while sunlit regions could experience subtle changes over time. This uneven heating and cooling could contribute to the unique features we see on Eris's surface, adding to the puzzle of its bright, reflective appearance. As we piece together the story of Eris's rotation, we gain a deeper understanding of how this distant world has been shaped by both internal and external forces. From its dense core to its interactions with Dysnomia and the lingering effects of ancient collisions, every detail adds to the rich tapestry of Eris's history. Next, we'll delve into how Dysnomia's gravitational influence might be affecting Eris's rotation and what this reveals about their fascinating relationship. Stay with us as we continue to uncover the secrets of this icy enigma. Now, let's take a closer look at how Dysnomia, Eris's moon, might be influencing the dwarf planet's rotation. The gravitational relationship between a planet and its moon is a delicate dance, and in the case of Eris and Dysnomia, this interaction could hold the key to understanding why Eris spins so slowly. Dysnomia's gravitational pull, though subtle, may be acting as a brake on Eris's rotation, gradually slowing it down over millions or even billions of years. This phenomenon, known as tidal locking, is not uncommon in the solar system, but it offers a fascinating glimpse into the dynamics of this distant pair. Tidal locking occurs when the gravitational forces between two bodies cause one to slow its rotation until it matches the orbital period of the other. In simpler terms, Dysnomia's gravity could be tugging on Eris in such a way that the dwarf planet's rotation is gradually synchronizing with the moon's orbit. Over time, this could lead to a situation where Eris always shows the same face to Dysnomia, much like how our moon always shows the same side to Earth. This process would explain why Eris's rotation is so leisurely compared to other objects in the Kuiper Belt. But what does this mean for Eris and Dysnomia's relationship? For one, it suggests that the two bodies have been locked in this gravitational embrace for a very long time. The fact that Dysnomia's influence is still detectable today points to a stable and enduring connection between the two. This stability could also provide clues about their formation. If dysnomia formed from a collision with Eris in the distant past, as some theories suggest, the gravitational interplay we see now might be a remnant of that ancient event. Studying this relationship could help us piece together the history of how Eris and dysnomia came to be. Another intriguing aspect of this dynamic is how it affects Eris's internal structure. The gravitational forces exerted by dysnomia could be causing subtle flexing within Eris, generating internal heat through a process called tidal heating. This heat, though minimal, might be enough to influence Eris's geology, potentially contributing to the presence of cryovolcanism or other surface features. While we don't yet have direct evidence of such activity on Eris, the possibility adds another layer of mystery to this already enigmatic world. As we explore the influence of dysnomia on Eris's rotation, we're reminded of how interconnected the solar system's objects truly are. Even in the distant reaches of the Kuiper Belt, the gravitational forces between a dwarf planet and its moon can shape their evolution in profound ways. Next, we'll turn our attention to another captivating mystery, the potential for cryovolcanism on Eris and what it could reveal about this icy world's hidden depths. Stay tuned as we continue to unravel the secrets of Eris and its place in the cosmos. Now, let's venture into another fascinating possibility. Could Eris be home to cryovolcanos? Unlike the fiery volcanoes we're familiar with on Earth, cryovolcanos erupt with icy materials like water, ammonia, or methane. These frozen eruptions could reshape Eris's surface, creating unique geological features that hint at the dwarf planet's hidden activity. The idea of cryovolcanism on Eris opens up a world of questions about what lies beneath its icy exterior. Cryovolcanism occurs when internal heat causes subsurface ices to melt and erupt onto the surface. On Eris, this heat could come from several sources. One possibility is radioactive decay within its rocky core, which might generate enough warmth to melt pockets of ice. Another intriguing source could be tidal heating, caused by the gravitational tug-of-war between Eris and its moon, dysnomia. As we discussed earlier, this interaction could create subtle flexing within Eris, producing heat that fuels cryovolcanic activity. If this is the case, Eris might not be as dormant as it appears. The presence of cryovolcanos would have significant implications for Eris's geology. For one, it would suggest that the dwarf planet has a dynamic interior capable of reshaping its surface over time. Cryovolcanic eruptions could deposit fresh layers of ice, smoothing out older terrain or creating new features like icy domes or flows. These processes could also release gases trapped beneath the surface, potentially forming a thin, temporary atmosphere. While such an atmosphere would be fleeting, it could still leave behind clues about Eris's composition and history. Interestingly, cryovolcanism has been observed or theorized on other icy worlds in our solar system. For example, Saturn's moon Enceladus is famous for its geysers of water ice, while Neptune's moon Triton shows signs of past cryovolcanic activity. Comparing Eris to these worlds could help us understand whether similar processes are at work on this distant dwarf planet. If Eris does have cryovolcanos, it would join a select group of icy bodies that defy our expectations of cold, lifeless worlds. Of course, confirming the presence of cryovolcanism on Eris is no easy task. The dwarf planet's immense distance from Earth makes detailed observations challenging. However, future missions equipped with advanced instruments could provide the data needed to settle this mystery. For now, the possibility of cryovolcanism on Eris adds another layer of intrigue to this already enigmatic world, reminding us that even in the farthest reaches of the solar system, there's always more to discover. As we ponder the potential for icy eruptions on Eris, let's turn our attention to another captivating mystery: how this distant world might have formed in the first place. What clues does Eris hold about the early days of our solar system? Stay with us as we explore the origins of this icy enigma and the secrets it might reveal about the cosmos. Now, let's take a closer look at how Eris stacks up against other dwarf planets in our solar system, particularly those where cryovolcanism has been observed or suspected. By comparing Eris to worlds like Ceres and Pluto, we can uncover fascinating parallels and differences that might shed light on whether this distant dwarf planet could also harbor icy eruptions. Ceres, the largest object in the asteroid belt, has provided some of the most compelling evidence for cryovolcanism in the solar system. Observations from NASA's Dawn mission revealed a mysterious bright spot in Orbital crater, which turned out to be deposits of sodium carbonate, a substance likely brought to the surface by cryovolcanic activity. This suggests that Ceres, despite its small size, has a geologically active interior capable of melting ice and pushing it to the surface. If a relatively small body like Ceres can sustain such processes, it raises the possibility that Eris, with its larger size and potential internal heat sources, might also experience similar activity. Then there's Pluto, Eris's more famous counterpart. When NASA's New Horizons spacecraft flew by Pluto in 2015, it captured images of towering mountains and vast plains of frozen nitrogen. Among these features were structures that scientists believe could be cryovolcanic in origin. One of the most striking is Right Mons, a massive mountain with a central depression that resembles a volcanic caldera. If this feature is indeed a cryovolcano, it would suggest that Pluto's interior is warm enough to melt ices and drive them to the surface. Given that Eris and Pluto share many similarities, both are icy, distant, and roughly the same size, it's not unreasonable to think that Eris might also host similar geological wonders. However, there are key differences between these worlds that could influence the likelihood of cryovolcanism. For instance, Pluto's surface is dominated by nitrogen ice, which is more volatile and easier to melt than the methane ice thought to cover Eris. This could mean that Pluto's cryovolcanic activity is more pronounced or frequent. On the other hand, Eris's higher density suggests a larger rocky core, which might generate more internal heat through radioactive decay. This could compensate for the challenges posed by its methane-rich surface, potentially making cryovolcanism just as viable on Eris as it is on Pluto. Another intriguing comparison can be made with Triton, Neptune's largest moon. Although not a dwarf planet, Triton shares many characteristics with Eris and Pluto, including a surface covered in nitrogen and methane ices. Voyager 2's flyby in 1989 revealed geysers of nitrogen gas erupting from Triton's surface, providing direct evidence of cryovolcanism. If Triton, which is even farther from the Sun than Eris, can sustain such activity, it strengthens the case that Eris might also be capable of similar processes. By examining these examples, we can see that cryovolcanism is not limited to a specific type of world or location in the solar system. Whether it's the asteroid belt, the Kuiper Belt, or the outer reaches of the Neptunian system, icy bodies seem to have the potential for surprising geological activity. For Eris, this means that the possibility of cryovolcanism remains very much on the table, waiting for future missions to uncover the truth. As we continue to piece together the puzzle of Eris, let's shift our focus to another captivating mystery: how this distant world might have formed in the first place. What clues does Eris hold about the early days of our solar system? Stay with us as we explore the origins of this icy enigma and the secrets it might reveal about the cosmos. Now, let's turn our attention to one of the most intriguing questions about Eris. How did this distant dwarf planet come to be? The mystery of Eris's formation takes us back to the chaotic early days of our solar system, a time when planets and smaller bodies were still taking shape. Understanding how Eris formed not only sheds light on its own history, but also offers clues about the broader processes that shaped the Kuiper Belt and beyond. One leading theory suggests that Eris, like many other Kuiper Belt objects, formed from the remnants of the solar system's protoplanetary disk. This disk of gas and dust which surrounded the young sun gradually clumped together to form larger bodies. In the outer reaches of the disk, where temperatures were extremely low, ices like methane, water, and ammonia were abundant. These ices likely played a key role in Eris's formation, helping to build its icy surface and potentially its rocky core. But what makes Eris stand out is its size. It's one of the largest known objects in the Kuiper Belt, second only to Pluto. This raises questions about why Eris grew so large and what conditions allowed it to accumulate so much material. Another fascinating aspect of Eris's formation is its relationship to other Kuiper Belt objects. Some scientists believe that Eris may have formed closer to the Sun, in a region where more material was available, before being scattered outward by gravitational interactions with giant planets like Neptune. This idea is supported by the fact that Eris's orbit is highly elliptical and tilted, suggesting it was once influenced by the gravitational pull of a larger body. If this theory is correct, it would mean that Eris's current location in the distant Kuiper Belt is not where it originally formed, adding another layer of complexity to its story. There's also the possibility that Eris's formation was shaped by collisions. In the early solar system, impacts between objects were common, and these collisions could have played a significant role in determining Eris's size, shape, and composition. For example, a major collision might have stripped away some of Eris's original material, leaving behind a denser, rockier core. Alternatively, collisions could have contributed to the growth of Eris as smaller bodies merged to form a larger one. The presence of Eris's moon, dysnomia, adds weight to this idea, as moons are often thought to form from debris created during such impacts. As we piece together the puzzle of Eris's formation, one thing becomes clear: this distant world is a product of the dynamic and often violent processes that shaped our solar system. From its icy surface to its rocky core, every aspect of Eris tells a story about the conditions and events that existed billions of years ago. And while we still have much to learn, each new discovery brings us closer to understanding not just Eris, but the origins of the entire Kuiper Belt. With this in mind, let's delve deeper into the role of collisions in shaping Eris's current form, and what these ancient impacts reveal about the early solar system. What can these cosmic crashes tell us about the forces that molded Eris into the enigmatic world we see today? Stay with us as we explore this next chapter in the story of Eris. Now, let's take a closer look at how ancient collisions may have played a pivotal role in shaping Eris into the dwarf planet we observe today. In the early solar system, collisions were not just common. They were a driving force behind the formation and evolution of countless celestial bodies. For Eris, these impacts could explain many of its unique characteristics, from its size and density to the presence of its moon, dysnomia. One of the most compelling ideas is that Eris's rocky core might be the result of a massive collision. In the chaotic environment of the early Kuiper Belt, it's possible that a smaller object struck Eris with enough force to strip away some of its outer layers, leaving behind a denser, rockier interior. This would explain why Eris has such a high density compared to other icy bodies in the Kuiper Belt. The collision could have also ejected debris into orbit around Eris, which eventually coalesced to form dysnomia. This scenario is supported by observations of other dwarf planets like Pluto, which also have moons thought to have formed from similar impact events. But collisions weren't just destructive, they could have also contributed to Eris's growth. In the crowded early solar system, smaller bodies frequently collided and merged, gradually building larger objects. Eris, with its significant size, might have grown through a series of these mergers, accumulating material over time. This process would have been particularly effective in the outer solar system, where ices were abundant and could stick together more easily. The result is a dwarf planet that stands out not just for its brightness but also for its sheer size, second only to Pluto in the Kuiper Belt. these ancient collisions also offer a window into the chaotic conditions of the early solar system. The fact that Eris's orbit is so elliptical and tilted suggests that it was once influenced by the gravitational pull of larger bodies, possibly even Neptune. A collision or close encounter with a massive object could have altered Eris's trajectory, sending it on its current path through the Kuiper Belt. This idea aligns with the broader understanding of how the outer solar system evolved, with giant planets like Neptune scattering smaller bodies into distant orbits. As we piece together the story of Eris's formation, it's clear that collisions were a defining factor. Whether they stripped away material, contributed to its growth, or altered its orbit, these impacts left a lasting mark on Eris and its moon. By studying these ancient events, we gain not only a deeper understanding of Eris, but also a clearer picture of the dynamic processes that shaped the early solar system. And as we continue to explore the mysteries of Eris, each new discovery brings us closer to unraveling the secrets of this distant world and the history of our cosmic neighborhood. With this in mind, let's shift our focus to another intriguing aspect of Eris: its potential for cryovolcanism. Could this icy world harbor volcanoes that erupt with frozen materials instead of lava? Stay with us as we explore this fascinating possibility next. As we reach the end of our journey through the 25 unexplained mysteries of Eris, one thing becomes abundantly clear: this distant dwarf planet is a treasure trove of cosmic enigmas. From its unusually bright surface and peculiar orbit to the mysteries surrounding its moon dysnomia and the tantalizing possibility of cryovolcanism, Eris continues to challenge our understanding of the outer solar system. Each discovery we've explored, whether it's the role of ancient collisions, the debate over its size, or the potential for a thin atmosphere, reveals just how complex and fascinating this icy world truly is. Yet for all we've uncovered, Eris remains shrouded in mystery. Its extreme distance from Earth makes detailed observation a monumental challenge, and many of its secrets are still waiting to be unlocked. What lies beneath its icy surface? Could there be geological activity we've yet to detect? And what more can Eris teach us about the formation and evolution of the Kuiper Belt? These questions remind us that the universe is full of wonders we've only begun to explore. The story of Eris is far from over. With advancements in technology and future missions to the outer solar system, we may soon uncover answers to these lingering questions and perhaps even stumble upon new mysteries we can't yet imagine. So, as we wrap up this exploration, let's stay curious. The universe is vast, and every discovery, no matter how small, brings us closer to understanding our place within it. If you've enjoyed this deep dive into the mysteries of Eris, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss out on our cosmic adventures. And remember, the next big discovery could be just around the corner. Until then, keep looking up. The stars have so much more to reveal.